This is the Chapter 7-8 commentary for the lipids section. So in this section, we're going to go ahead and focus on the lipids chapter, Chapter 8. So in this slide, we go ahead and we see a breakdown of lipids. So fairly straightforward. Just like the biochemistry section, this is going to require a lot of memorization. It'll also require a lot of categorization. So in this case, you're going to have to memorize each of these names, as well as be able to classify. So, in the next series of slides, I'm going to go ahead and head in this direction, where I start with lipids. I go through saponifiable lipids, starting off with simple, and then I go to explaining different types of saponifiable lipids, simple lipids, waxes, triglycerides. Afterwards, I'll start going into complex saponifiable lipids, such as phosphoglycerides, and then sphingolipids. Afterwards, I'll go ahead and I'll go through non-saponifiable lipids, such as steroids and prostaglandins. Through each of these, I'll go through examples. Some of them you'll have to memorize, some of them you'll just simply have to recognize, and then all of them you'll be responsible for categorizing. In this case, lipids are a biological compound that are soluble only in nonpolar solvents, and they're categorized by their structures and properties. Think of, in general, lipids are the biochemical fats. So we're going to be just looking at fat molecules. The first category is saponifiable saponifiable liquids versus non-saponifiable lipids. So let's go ahead and go through those general categories: saponifiable versus non-saponifiable. Here is an example of a saponifiable lipid. Basically, a saponifiable lipid is any type of lipid where there is a acid or ester that's present. And what happens is, if you have either an acid or acid present, and you go ahead and you add in a base, such as potassium hydroxide, then you can have saponification start to occur, in which case the acid or ester, and usually we've only seen this for esters, will actually break apart in a saponification. And I'm probably off by my hydrocarbons, but and it'll form a acid salt. So there are various types of lipids which have this type of ester, or they'll have an acid, and if you combine a base such as potassium hydroxide, it'll form an acid salt. So this will be considered a saponifiable lipid. Compare this to a non-saponifiable lipid. A non-saponifiable lipid, and I'm just going to go ahead and make up one. This is a type of what they call a prostaglandin. This is a short-range hormone lipid. Consequently, do you see any acids or esters that are present? Nope. So if I were to sit there and add in potassium hydroxide, a base, no type of reaction would occur. So we say that this is going to be non-saponifiable. Steroids are another example, and those are non-saponifiable lipids. So let's go back to our slides. So saponifiable contains an ester. This can be hydrolyzed under basic conditions, such as with a base. I should also point out that it's not just esters that are classified as saponifiable, but anything that is also containing an acid, such as fatty acids. So we're going to go ahead and go down this direction right here, saponifiable lipids, and then we're going to go to another subcategory called simple lipids. These contain only alcohol and fatty acid components. So these are fatty acids, which I'm highlighting right here. You will have to memorize these fatty acids. Now, in biochemistry, every unique structure and its resulting unique isomer has a unique common name. So, in this case, this structure right here has the common name palmitic acid. The names themselves don't really offer insight into the structure. Rather, they're either from the origin or they're from the function that they were discovered in. So many different backgrounds when it comes to the name. At this point, you simply have to memorize it. In this case, this is a 16-carbon acid. And because it's used in making triglyceride fats, we call this a fatty acid. Notice how it ends in a obvious carboxylic acid with a really long tail. So again, it's composed of 16 carbons. You can go ahead and count them as you want to. That's palmitic acid. Go to stearic acid. It contains 18 carbons. So the only difference between palmitic and stearic acid are these extra 2 carbons that you see right here. So extra 2 carbons here. Oleic acid has 18 carbons. The only difference is if you were to count down to carbon 9, you would find a double bond. Now, it prefers to have it in the cis form. There is a trans form of oleic acid, but the body prefers the cis form. Think of cis fatty acids versus trans fatty acids as qualities of gasoline. Although your car can function on both 87 or 92 premium gasoline, it prefers to have the 92. It's a cleaner burning fuel. Same thing with cis and trans. The body prefers to have cis over trans. It's been a big marketing ploy to tell you how there's no trans fatty acids. You could have both, although the body does prefer cis. In this case over here for linoleic acid, it's a diunsaturated fatty acid. In this case, on carbon 9 and carbon 9 and carbon 12, counting from right to left, we have 2 cis double bonds. And then if you take a look at linolenic acid, we have one at 9, we have one at 12, and then we also have one at 15. So we have 3 cis double bonds. Crazy. Now, these right here, which I'm highlighting with my yellow pen, these right here are what we call the essential fatty acids. We call them essential fatty acids because we need these from our diet, from eating. We cannot make these naturally in our body. So we call these the essential. These over here, these are the non-essential. Although we could get them from our diet, we can actually synthesize them on our own if we wanted to. And finally, although I'm not testing you on this other form of naming, nutritionists have their own way of categorizing these fatty acids, and they could classify it the monounsaturated or diunsaturated or the triunsaturated this way. If you think of the carboxylic head as a beginning, that could be considered the alpha. If you consider this very last carbon the N, that could be considered the omega. And what's going to happen is if we were to sit there and count from the omega side, carbon 1, 2, 3, 4, 5, 6, 7, 8, 9, oftentimes this is referred to as a omega 9 fatty acid. And I don't like the symbols for this, so I'm just going to use the word omega. Omega 9 fatty acid. And that shows where the double bond is, counting from the N carbon or the omega carbon, going from left to right. Consequently, for linoleic acid, this has been categorized as the omega 6,9 fatty acids, and if you look at the very bottom, this has been categorized as the omega 3,6,9 fatty acids. So, on various food products, oftentimes they'll talk about how, yes, these contain the essential omega 6,9 and 3,6,9 fatty acids, in which case it includes the linoleic acid and linolenic acid. I do want to point out that there are other types of fatty acids. These are the main ones that you need to know, and they're the easiest ones to memorize. Let me go ahead and focus on the omega 6,9 and 3,6,9 fatty acids, aka linoleic and linolenic. So again, these are essential fatty acids. This is the condensed form, although if I test you on it, in general, I like the line structure. You should by now see the pattern. All of these are even numbered carbons, and obviously they can be saturated, such as stearic acid, or they can be unsaturated, such as the essentials, linoleic and linolenic. Again, you'll need to memorize all of these. Most of these essential fatty acids tend to be found in plants or fish oil. Alright, so let's go into some of the physical properties. Rather than boiling point, we're going to be focusing on melting point. Melting point. And here is the general idea. If you take a look at stearic acid, it is roughly in a straight line. However, the minute you start having double bonds, then what will happen is you'll start to have a kink or bend to the fatty acid. Take a look at this fatty acid to the far right. It has two double bonds, so you have a major kink factor, so to speak. Now, if I were to sit there and I'm just going to draw a general fatty acid, no one in particular. So in this case right here, I have a saturated fatty acid. Notice double bond, no double bonds. Consequently, these fatty acids can actually get really close to each other, and we can say that they stack quite well. Compare this one to the unsaturated fatty acids that you see down here. So in this case, if you notice how I'm drawing this, even though it's quite messy, compare the unsaturated versus the saturated. And what you'll notice is there's a much bigger gap when we try to stack the unsaturated fatty acids compared to the saturated fatty acids. So notice there's a smaller gap for saturated fatty acids versus the unsaturated. Now, this is important because when you're stacking saturated fatty acids, if there's less of a gap, then the fatty acids can stack closer. They therefore have much stronger intermolecular forces. Because they can get closer to each other, the intermolecular forces have a greater play. Therefore, it has a much higher temperature at which the fatty acid melts, so much higher melting point. On the other hand, if you have a bigger gap, and let me go ahead and finish drawing in the double bond. So if you have a much bigger gap, because it can't get as close, due to the kink factor of the double bonds, creating this weird arc in the tail so they can't stack as close. So the fatty acids stack farther away. I know I'm writing messy. Then you have much lower intermolecular force. Now it's getting kind of messy, so let me rewrite this part really good. I'm going to use my pen. So, with a bigger gap, the fatty acids stack farther away from each other. So therefore, due to a farther distance, they have lower intermolecular force attraction between each other. Consequently, they have an overall lower melting point. So the take-home message in this is the more double bonds you have, the bigger the gap. The farther away the distance between the fatty acids. Consequently, they stack farther away, the lower the intermolecular force, and the lower the melting point. So the melting points decrease as the number of double bonds increase. So they have an inverse relationship. So make sure you know that. Now, fatty acids have and I'm just going to go ahead and highlight one fatty acid, and this is just a crude picture. Here is one fatty acid that I'm highlighting. So it has a polar carboxylic head, and it has a nonpolar. I'll just go ahead and I'll circle this. I better circle it with a red pen. And it has a nonpolar hydrocarbon tail. So when you start putting fatty acids in water, this becomes an issue because water is polar, whereas a fatty acid has a polar head and a nonpolar tail. What often happens is the fatty acids will form what's cleverly called a micelle. A micelle. And micelles are spheres of fatty acids. And what happens is the fatty acids situate themselves so that the nonpolar tail of the fatty acids point inward inside the sphere, as you see me highlighting right here. Whereas the polar head actually points outward, so that way the polar is attracted to the water. Now, when it does this, we say it has specific properties where the polar section, which is attracted to the water, we say it's hydrophilic. Hydrophilic. Philic means it likes it. So hydro is water, so it likes the water part. So the hydrophilic portion of the fatty acid sticks out. The part that doesn't like the water, the nonpolar part, we say it's hydrophobic. Phobic. So phobic means to not like. So the hydrophobic part, it points inward. So you'll be responsible for drawing a crude micelle, drawing something very simple like this with the hydrophobic tails pointing inward and the hydrophilic heads pointing outward. So make sure you can draw this high-tech sketch right here. Let's go ahead and move on. Now, we talked about fatty acids for saponifiable simple lipids. Now we're going to go into waxes. Waxes are very straightforward. They're essentially very, very, very long hydrocarbon tails. And then they have a central ester in the middle, and then they have a really, really long continued hydrocarbon that's connected to the previous alcohol portion of the ester. So basically, it's an ester with long hydrocarbons on each side of the ester. Why does it do this? Well, it turns out these really long hydrocarbons on these esters are very nonpolar. Let me change pens. They're very nonpolar. And this is done on purpose. The more nonpolar it is, then this will actually create a very nonpolar surface, which I'm repeating myself, I know, and it makes it highly waterproof. So we tend to find these really long hydrocarbon tails on these esters on each side in waxes. So for example, you have these type of really long esters that make up the wax of leaves, for example. because technically leaves need to be waterproof. They do like water, but they don't want to sit there and have water in places that are not appropriate. So they tend to be covered in a very thin wax. So I think I'm making more out of this than it is because it's very straightforward. Waxes are water insoluble because they have these really long hydrocarbons on each side of the ester. So go ahead and take a look at beeswax. It's actually a mixture of these various types of waxes. Notice how long each of these hydrocarbons are. So it's obviously mostly nonpolar, therefore it makes a very nice waterproof coating. You're not responsible for memorizing these names. You are responsible for generating a very crude wax. I could say sketch any wax, in which case you make these really long hydrocarbons on each side of the ester, and that's good enough for me. Also know the general definition of a wax. So memorize the definition and general purpose. But I'm not going to ask you to make any of these actual names. Let's go ahead and move on. Make sure you memorize these two categories of